Uh, Very good morning to all of you. So this is the lab session 2, or we can say video recording for lab session 2. So as we can see, so we are performing this video recording on the virtual lab. This is the site you can note down. It's iitlab.ac.in. It provides the different virtual lab features. Okay, so if we are see the list of experiments, so which I already discussed in the first lab. So these are the list of experiments that is available in this course of virtual lab. Fine. So in the previous lab, we have discussed the image arithmetic. Okay, what are different arithmetic operators that can be performed on the image. So basically, we have seen five different types of operators. That is your addition operator, subtraction, difference, multiplication, and division operator. Then along with that, we have also considered how we can auto scaling and clipping properties. And then we have analyzed some of the case tools, and we have seen how the images can be managed. Okay, so now today we are going to perform the second experiment, which is your Fourier transformation. Okay, so let us start the Fourier transformation. Now, this is the objective of your experiment, you can say. The main objective of the experiment is to understand some of the fundamental property of Fourier transformation. Okay, so as we are already discussed in the class, so basically Fourier transformation is the different format of representing the images. Okay, like we can say any numbers. Okay, now we say number can be represented in a decimal format, in a binary format, or in a hexadecimal format, in a octal format. Okay, similarly, the images can also be represented in different formats. So one of the formats that you are very familiar with is your, you can say your spatial domain representation, where we represent it in the terms of pixels. Okay, and each pixel is having a coordinate x and y, and f represent your intensity level at the pixel. Okay, now similarly, the second way of representation is called your Fourier transformation, where basically we represent the image in terms of, we can say in terms of frequency. Okay, so basically signals. Okay, this is a different type of representation of signal. Okay, whenever we talk about signals, how these signals can be represented. Okay, so in this lab, basically we learn how we will convert a given image. Okay, if certain image is given, how could I convert this image to the Fourier transformation? Or we can say how I can convert the image to frequency domain transformation. Fine. So let us move to the introductory part. Let us understand the theory of Fourier transformation first. So as I said, a number can be represented in many ways. Okay, like a number can be represented in many ways, such as in decimal format, or in a binary format, or in a hexadecimal format. Okay, so similarly, the signal can also be represented in many ways that are more convenient for certain type of analysis. So first of all, the question rises why we have to transform to the another domain. Okay, but the question rises here why we need to transform a signal from one particular domain. So if I say this is my one domain, fine. So this is my suppose time domain. If I say this is my time domain, fine. And if I want to transform this signal, applying some transformation, so I will write of that xt. Now f will be your any type of transformation, fine, of xt. the question rises here, why we should convert? Why we convert from one domain to another domain? Okay. Now, because first reason we can say that the reason of converting to one domain to another domain, the analysis in a frequency domain are much easier than compared to the time domain. Okay. The second thing we can say, the computational time. Okay, the computational time will be much less compared to the time domain. So whatever the computational time required in the frequency domain, this will be much lesser compared to the your time. And third thing, we can say some of the properties, like we can say the convolution in a time domain can be computed a multiplication in a frequency. So whatever result you get by convolution method in a time domain, the same result you will get when you perform the multiplication in your frequency domain. So what will happen? So it is having some better features, okay, than your time. So that is the reason convert the signal, okay, signal except P to one domain to the another domain. Fine. So what we have said, like number are represented in a different format. Okay. Similarly, the signal can also be represented in many ways that has more convenient for certain type of analysis. And the most common representation is the Fourier transformation, which convert your spatial domain into the spatial frequency domain representation. Okay. So what Fourier transformation do? A Fourier transformation will simply convert your spatial domain image. Okay. You can say it will convert a spatial domain image to the spatial frequency domain representation. Right? The Fourier transformation, which is written as FT, is a way of expressing the image A in terms of set of pure sinusoidal function. Sinusoidal means sine and cosine function. Okay, the pure sine and cosine functions. It transfers the image from spatial domain to the frequency domain. Okay, so what actually is do? So whenever you apply the Fourier transformation, so first of all, it's express the image is in terms of pure sinusoidal function. That means whatever the image will be get, the signal will be constructed with a basis function, and that basis function are basically your, we can say, the sine function and the cosine function. Fine, and it transfers the image from a spatial domain to the frequency domain. And if Fourier transform image, okay, so whenever we perform Fourier transformation for image, each pixel represent particular frequency contained in the spatial domain. Like in the spatial domain, what we are having now, suppose this is my representation of image in spatial domain. Now each pixel, if I consider the each pixel here, okay, if I consider each pixel, suppose if I consider this pixel P, or this pixel P here, this pixel P in spatial domain basically represent a coordinate x and y. Along with this P will represent some intensity. But what happened in frequency domain? Okay, now each pixel in the frequency domain P is particularly contained, we can say it represents a particular frequency contained in a spatial domain. I can say this coordinate x and y, okay, will represent a particular frequency. Now this will have some particular frequency. Right? So that's the reason we say when you convert from one domain to another domain, the size of the image will be unaffected. Okay, the size of the image will not be going to change. It will be remain same. If there is n number of pixels, or we can say it is n cross n size in your spatial domain, then when you convert to the time domain, so when I converted it to a time domain, then what will happen? The resultant image will also be n cross n. Okay, and number of pixels will be same. Number of pixels will be same. Okay, so this is the introduction part about what you understand by Fourier transformation. Hope it is clear to all of you. That means what is Fourier transformations, why we need to perform a transformation, okay, and what actually happens so when we will perform a Fourier transformation. So I think it is clear to all of you. this is the introduction part for FFT. Sometimes it can say forecasting the FT. Okay. So then we will perform the Fourier transform of the discrete signals because the images are basically stored in discrete format. Okay, so we will perform a transformation for discrete signal. So on that case, we will say discrete Fourier transformation. We will represent as DFT. Okay, DFT stands for your discrete Fourier transformation. Fine. So let's move on to the theory part. Okay, so we'll move on to the theory part. So let me quickly explain the theory part. So as we are interested in digital image, okay, so as we are only interested in the signal which is basically discrete in nature, that means as we are already discussed, the digital image are stored in a discrete signals. So we concentrate on discrete Fourier transformation. That is DFT. So as I already said, we will only interested on the discrete Fourier transformation. Okay, so it can be used a broad range of applications such as now this Fourier transformations can be used for the applications such as filtering, okay, removal of noise, we can say noise filtering with some high pass filters and low pass filter. Then image restoration, that is how to restore the image to its original format. Then image compression, so whenever we need to send the data in low bandwidth, okay, so we need to compress the image. So we need to basically compress the size of the image. Now this compression can be performed with the help of image compression technique. Then for analyzing, okay, for human perception point of view, we can perform a different analyzing purpose also. That is the main reason for why we are performing the Fourier transformation. Then we can say the DFT does not contain all the frequency which forms the image, but only some sample which are sufficient to represent the information of spatial domain. So first point, we have to note that now all whenever we perform a DFT, so it does not mean that the entire image is converted to your frequency domain. So what will happen? Some portion of the pixels or some part of the picture or certain pixels of the sample will be converted into the frequency domain. Now that part will be sufficient to represent the information in your spatial domain. Okay. Now given for a given image, suppose I will say this is my given event f of n comma n. Now it is of a size, I have to say it's size of n comma n. Then the mathematical expression for the DFT and inverse DFT. Now inverse DFT is basically used to retrieve back the original image from the we can say frequency domain. Okay, so IDFT basically we say IDFT. Now this IDFT are used to get back the original image. Okay, so the mathematical formula, as you can see how it is expressed. Now this is a mathematical formula for DFT, which is given by we can represent in the frequency domain capital F of KL, which is the frequency domain representation, is nothing but summation of m equal to 0 to n minus 1, then summation of n equal to 0 to n minus 1. Now this is my original image. Then e to the power of minus 2 pi multiplied by k m small m divided by capital M plus n L divided by capital M. Okay, so now this is equation number 1 is given for your DFT. Similarly, we can derive the original image, which is your f of mn. Okay, now how it is derived? So with the help of IDFT, now we can say it is nothing but 1 by 1 upon capital M by capital N and double summation. Now m varies from 0 to n minus 1, then n varies from 0 to n minus 1. Now this is your f of KL. Okay, now it is e to the power of 2 pi km divided by capital M plus nl divided by capital M. Now equation 1 can be interpreted as the, now we can say the equation 1 is your value of capital F of KL at each point is obtained by multiplying the spatial image with the corresponding exponential base function. Okay, so how the each point, now let us say f of kl. Okay, now f of kl, fine. Now how this each point of f of kl is obtained? Now suppose this is my representation of f of kl. Now this each point of f of kl is basically obtained by, so how we obtain? Now we basically multiply the each point of original image of f of n. It is multiplied by the basis function. Okay, now there's a basis function here. Now where the here basis function is your exponential function. The multiply with the corresponding exponential function, which is your base function. Now it is followed by summations. Okay, now the base function are pure. Now you have to understand this base function are purely sinusoidal because we can say this is sinusoidal with increasing frequency. Okay, now it is basically derived. Now when you expand this one, it is in the form of minus e to the power of we can say 5 ut. Now when you expand this one, it will be something sine theta plus I cos theta. And so that is this is pure sinusoidal with the increasing frequencies. Okay, now coming back to equation 2. Now coming back to equation 2. Okay, so what the equation 2 basically is IDFT. So 1 by n is term corresponding to normalization constant. So while we are multiplying this 1 by mn, so because to normalize the constants, so we have to multiply it, and the output of f of t image is a complex value image which can be displayed by two images. Now what happens? So whenever we transform the original image to the Fourier transform with the frequency domain, now your output is basically represented in two different types of image. One is called magnitude spectrum or magnitude image. Second one is called your frequency spectrum or frequency images. Okay, now this is a very important point. Now whenever we represent unique image, or whenever we perform FT or DFT, now this basically converts the original image into two different types of image. One is called your magnitude of the image. Second is called your phase angle or phase of the image. Okay. Now often only the magnitude of FT is displayed because it consists of most of the information about the geometrical structure of image in spatial domain. So what happens in the most of the cases? The most of the cases, okay, the most of the cases you will find only one image, okay, and that basically represent your magnitude of ft, okay, which display, okay, or we can say which consists of most, because the magnitude is the main part of FFT, which consists of most of the information about the geometrical structure of an image in a spatial domain. So whatever information they are having in spatial domain, the magnitude spectrum will have the most of the information. Fine. Now it is very easy to examine the process. Okay. Now with certain frequency of image in Fourier domain, and it influences the geometrical structure of spatial domain. Or we can say in general, the Fourier transform image is shifted in such a way that the DC value, okay, we can say image mean value f of 0, 0 is displayed in the center of the image. The distance from the center is proportional to the corresponding frequency. So what I can say, as we know, the image is basically represented by the origin, 0, 0. So whenever you perform the Fourier transformation, this value is shifted to the, this mean value is shifted to the center of the image. So when you perform FFT, so or DFT, this center is shifted to the, or this mean value of 0, 0 is shifted to the center, and rest of the frequency is fine, nothing but distance from the center which is proportional to the your basical frequency. Okay, so here it is example. So let us explain with an example, understand with an example. So it's more further clear. So this is a very popular picture for image processing. The name of the image is Lina's image. Okay, so most of the time we will use this image for the image processing. This is very popular picture. So now in this example, what we have performed, now this is an example. Here we show the spatial. Now this is my spatial domain representation on the left of side. Now you can see on the left of it, this is my spatial domain representation, and right of it, this is my frequency domain representation. Okay, this particular image is called Lina. So what happened here? The image source on the right hand is a magnitude spectrum. Now this is called your. This is basically your magnitude spectrum, and it is having most of your what we can say most of your information, most of your geometrical information. Fine. So magnitude spectrum calculated from the complex result of Fourier transformation. So what the value of the magnitude spectrum? If you know, it will be given by the mod f. Now it is nothing but it is root over r square plus imaginary part r square. Okay, this is your formula for magnitude spectrum. Because as we know, Fourier transformation represent in relative terms. So R represent your real part, and I represent your what? Imaginary part. Okay. And the we can say the DC value. Okay, the DC value of which is your mean value, we can say f00, can be represented by the brightest spot of the image. Now this is can see the brightest spot of the image. Now this is the actual coordinate of 0, 0. Okay, which is changes to the center of the point. But however, the dynamic range of the Fourier coefficient, that is intensity value of the Fourier image, is too large to display on the screen. Therefore, all the values appear as a black. So why it is appearing black? What is the reason? Why it is appearing black? Because now to represent this one, okay, the intensity value will be too large, okay, too large to display. Therefore, all the value that is appear in a black. Now, if you apply the algorithm logarithm compression to this image, okay, we will get like this, or this will be actual. Okay, fine. Why we are getting black? Because it is very difficult to represent all this pixel in frequency domain. Okay, now the Fourier coefficient, that means the Fourier coefficient is too large for displaying on the screen. That is the reason it's appearing in the black. So when we are performing logarithm, that means we are now reducing the volume, because whenever we are performing the logarithmic operation, so what basically we will do? So we will reduce the intensity. So when we reduce the intensity, so you will get an image like this. This is the actual image that will be going to get. Now this is your magnitude spectrum. Now here you can see the at the center. Okay, here at the center you can analyze center of the image. This is my brightest part. Okay, which is your coordinate. This is will represent your coordinate. Therefore, 0, 0. And rest of the pixels or intensity level is find directly proportional to the frequency of their distances from this center. Okay, so I hope it is understandable to all of you. Okay, so let us continue. So what happened? The above image contain the components of all frequencies, but the magnitudes get smaller for higher frequencies. Fine. So the above image basically consists of all the frequency of ranges, but if you compare to the magnitude, which is much smaller for the frequency, hence lower frequency contain more image information than the higher. You can say the lower frequency is containing the more information than the higher. And the transformation image also let you understand two dominating direction of Fourier images, one passing vertically and one passing horizontally at the center. Okay, now you can imagine the two lines are passing through it. One passing horizontally and another is passing vertically. Now these two lines are dominating in this two directions. Okay, now similarly, this is my, you can see this is my phase spectrum for the greenhouse image, okay, as shown is in the figure. Fine, and the value of each pixel represented by the phase corresponding to the frequency. So what is my phase angle corresponding to, now this phase angle is basically given by tan theta equal to tan inverse, okay, it will be imaginary part of UV by real part of U. This is the formula for finding the phase angle of any corresponding. Fine. Now, if you apply the IDFT on the magnitude spectrum while ignoring the phase, okay, suppose you will perform an IDST on only magnitude spectrum, so you may not be getting the original image. The image will be in something like that. Okay, so you may get an image of this form. Why which is so? We are not included. The reason is we are not included your phase angle. Okay, so we can say although the above image contain all the frequency same as the original image, Nina image, so it is corrupted. So this shows that the phase spectrum plays a very crucial role in image reconstruction. So what we can conclude? So we can conclude from this statement that to reconstructing the images, the phase angle plays a very vital role. Okay, if you ignore the phase angle, okay, if you ignore the phase angle, so it may be a cause that you may not get the original spectrum. Fine, or we can say we cannot get the original reconstructed image. So we cannot going to ignore that part. Okay, so whenever you want to reconstruct the image, then you have to consider your magnitude spectrum as well as your phase spectrum. And the phase spectrum in an audio or image signal contain very important information, and any manipulation there can destroy the identity of the signal. This is the why people don't touch the, or we can say touch in the filter or go for linear phase filtering. Okay, so if you change any of this phase filter, okay, then it will not going to give you the value. So that is the reason most of the time we will not going to change the phase spectrum. Okay. So let us see some more familiar images that we will going to use in your image processing. So this is another very familiar image. Okay. So this is two-dimensional Fourier transform representation of image as a summation of sinusoidal function, that is basic functions, and the Fourier transform of pure sinusoidal image are simple as follows. Now, as you can see, this is my horizontal sinusoidal image. Okay, this is my horizontal, and this is my vertical sinusoidal image. So when I perform the DFT over it, okay, so you will get an image of like this, which is basically your magnitude spectrum. Okay, this is basically your magnitude spectrum. Okay, we will now not consider about the spectrum. Now you can see here the horizontal line bars are converted to your single dotted line. Now this single dotted line basically your source, that is your pure basic sinusoidal image. Similarly, when you convert your vertical sinusoidal image, okay, so this is my vertical sinusoidal image. So when I convert by using the DFT, right? So what we get? I will get this one as again. This is my spectrum. Okay, magnitude spectrum. Now it is now you can see it is represented by a vertical line. Okay, with this dot basically represent your higher intensity values. Okay, this line. And so these two are very important relevant to how to convert horizontal sinusoidal then its respective DFT, then how to convert the vertical sinusoidal and their respective DFT, how the DFT is used. Okay, let's move. So we can say from the above figures, we can observe that the Fourier transform of pure sinusoidal image in a single component represented by two bright spots symmetrically placed about the center. Now you can see when the both are very similar, okay, but one is horizontal, one is vertical, and they are having two bright spots. Now this is again very important image of cameraman, to which we are going to frequently use. Now this is a Fourier transformation of this cameraman. Okay. Now this Fourier transform cameraman image shows in above, and you can notice that image that's shown in the right are magnitude spectrum of this one. Now this is our magnitude spectrum. Now this spot, white spot, is because it is the main coordinate f equal to 0. That is the reason we are displaying as a brightest spot. Okay. I hope it is clear still now to everyone. So let me finish the theoretical part in this session. And in the next session, I will show you the procedure how we can say how we can implement. Okay, so about the frequency domain filtering. Now there are certain properties that are associated. Now you can see the frequency domain filtering. So in this section, we saw some filtering effects in the frequency or Fourier domain. Okay, in the frequency domain or Fourier domain, we can say the frequency domain filtering takes place an image and filter function in a Fourier domain, and this image is then multiplied with the filter function by pixel. Fine. Now suppose this is my filter function, I could say. Now this is my original image setting. Now it is multiplied by your f of kl and h of kl, where g, h, and f are Fourier transform of filter image. Okay, and input image and filter respectively to apply to obtain the resulting image in a spatial domain. Now here we have to what has to be transformed during the IDFT. Here are some example of, now you can see below there are some examples also given. So let us first discuss about what you understand by low pass filter. Now this is my original image. Okay, so I say this is my original image. So we can say this is our actually frequency domain. Then I apply the low pass filter. So this is my image which is obtained by using the low pass filter, and this is the second image. We are use another type of filter. Now in the first and second image are original and FFT of Lina, as I already said. So this first image your original image, and this is your FFT. But the third is obtained by multiplying the complex Fourier image with the image containing circle of radius 50 pixels. Okay, so how we obtain this image? Now this image is basically obtained. Now we are multiplying. Now this we are basically multiplying this image with an image that containing a circle of radius 50 pixels. So after applying the IDFT on the third image, we get the rightmost image, which is your we can say low pass filter image for the given. Okay, so what we have done, original this is DFT. Now what I have done, I have multiplied and I can say I have multiplied a circle of radius 50 pixels image with this my original image. So once I convert this to your IDFT, I will get my image in this manner. So we can say this is my low pass filtering images. Fine. Now similarly, you can perform the second example. Similarly for high pass filter, okay, for the high pass filter we can obtain by subtracting the value of TCO Fourier series as given below. Now this is my original image. This is my, you can say original DFT. Now while multiplying with the high pass filter. Okay, we'll get image like this. Now when you perform an IDFT, this will be your final image. Now this is our low pass filter. Okay, when you multiply with low pass filter, or we can say low pass filtering, and this is obtained when we are performing with high pass filter. Okay, so with this we have finished the theoretical part. Okay, so as the time is also going to the end, we have 2 minutes left. So let me recall what we have learned today. So basically we are performing the experiment. The main objective of the experiment is to find the Fourier transformation of a given image. Okay, so then we have learned about the introduction part. So introduction part we have discussed why we need a Fourier transformation. Fine. Then we discussed in detail theoretical part, that is we discussed in detail the mathematical formulas for Fourier transformation and for inverse Fourier transformation. Then we discussed some of the examples of Fourier transformation. Then we see in Fourier transformation how crucial the phase angle or phase spectrum play. Okay, and what is the role of magnetospectrum. Then we have seen some familiar examples on which we derive the Fourier's magnetospectrum and Fourier's phase spectrum. Then we have discussed some familiar figures like horizontal sinusoidal figure, vertical sinusoidal figure, and the famous figure of cameraman, how we converted this one and what we done. Then we have something discussed about filtering or frequency domain filtering. So here we discuss about two types of filtering. One is your low pass filtering. Then we applied that low pass filtering in very famous image, and we analyze the result of low pass filtering. Similarly, we discuss about high pass filtering. Okay, so now again that by applying high pass filtering, we have discussed how this result can be made. So we will, I think, we stop here.